Okay, so good evening, students. Again, this is Dr. Dong, and today we're going to learn process scheduling. The topic is process scheduling. So last week we mainly learned the topic of interprocess communication, and we said that there are three approaches, which are shared memory, message queue, and socket. So among these three approaches, we say that shared memory is the most is the most efficient, whereas there could be some conflict. Uh, so access conflict. This thing happens when two processes try to write into the same area of their shared memory, and then so you don't know who should get the access to that area first. This is like if two people share the same car and at a time when they both of them want to use the car, then there is a conflict. Whereas message queue is relatively slower, but so there is no conflict. And so for socket, we say that normally we use a pair of sockets as a pair of agents or representatives for two processes on two different computers or hosts to communicate. However, it's possible that we use this for two processes that reside on the same computer. That is also fine. And so in that case, we just use socket for interprocess communication. And even though this is not very usual. Okay, so today our main topic is process scheduling algorithms, which is this part, and and also from this part you are going to have your first homework one. So pay attention, and because it saves your time if you pay attention to this lecture. So first let's let's look at let's learn the motivation of process scheduling. So previously, I think in a second video lecture, I talked about a concept named multi-programming. So multi-programming is like, even though we only have a single CPU, but we allow multiple programs or processes to run. So this is like, so we have a waiter, a single waiter in a restaurant, who just rotates between different tables to serve all the customers. So similarly, it's like we have a single CPU, but we have different processes, and then this CPU just quickly rotated between all these processes, and so that we get a feeling like as if all these processes are executing at the same time and all the time. But actually it's not, because we only have a single CPU, and it is only able to handle or run one process at a single time. So here is the problem. So when we have multiple processes to run, to run, and we only have one CPU, so the question is, who should be able to take control of, to go to the CPU to run first. So we need to make a decision, and also we need to make a decision. Say process one grabs the CPU, and it is able to run. But also we need to know the other thing that we need to know is like, how long can we allow this process to run. So we don't. So for example, if you go to a restaurant, and if you are taking this waiter's time for too long, the waiter may say, okay, Mr. or Mrs. With your name, and sorry, I have to serve the other table. I will come back to you later. Right? So to make sure that the other people or the other customers do not wait for too long time. Similarly, here we also need to decide, okay, when should we make a stop, let the CPU stop when it's executing a process, even though that process is not finished, so that the other processes do not need to wait too long. So this is the motivation and at this time we need to basically schedule or to make a schedule for the CPU. And so at this time we are going to need an algorithm named CPU scheduling algorithm, which decides, okay, so who is going to be executed next and how long can the process run. So and before I'm going to before that I'm going before introducing this detailed CPU scheduling algorithms. So I want to briefly introduce a couple of concepts. The first one is called CPU burst and I/O burst. So actually let's imagine, okay, so for now you're just say playing no sending a message to your friends. So and you're just exchanging messages with your friends. So for 1 second you're just doing typing, and then you send, and typing and send. Okay, so this is like the circle, and at the time when you are doing when you are typing in your words, or typing your texts, actually at this time your CPU does not need to run at all. Only the keyboard is responsible for accepting your inputs. So at this time we call it's a I/O burst, so meaning that during this time all of the work are input and output. And then send, so after you say, okay, I'm done with my typing, I'm going to send this message to my friends, and at this time your CPU is going to run, okay, to execute the sending program, so that your friends can receive your message. So and then this here we call it a I/O burst, sorry, a CPU burst. And then after that we have another I/O burst and another CPU burst. So actually almost all processes just rotate, switch between I/O burst and CPU burst. So for example, when you are playing video games, it's the same, okay? So you're like typing in some commands from your keyboard. At this time so you're in the process, or the game is in I/O burst. Whereas when you finish typing in, and then the CPU is going to send your command to the remote server and also display something for you, and that is called CPU burst. So 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 here, based on how long is the CPU burst and how long is the I/O burst, we can just categorize processes into two types. The first type is called CPU bound process, and so for example here, okay, we have a CPU burst, and then we have a long CPU burst and followed by a short I/O burst, and a long CPU burst followed by a short CPU I/O burst. So here we say that this process is going to rely on the CPU intensively, and we call it CPU bound process, because it spends more time doing computation rather than input and output. So whereas like for the other processes which have a short CPU burst but long I/O burst, we call them the I/O bound processes. So so here we're just describing I'm just showing the distribution of the CPU burst durations, like how long is the CPU burst. And here I'm just this is the data from more than 10,000 processes. Over here we can see that a majority of the x-axis is just the burst duration, whereas the y-axis is just showing that how many processes have this period of or this burst duration, or the frequency of this burst duration. So here we can see that a majority of the processes have a relatively short CPU burst time, less than less than or equal to 4 milliseconds. So this means that even though most of the processes when they need the CPU, they in most cases they are only going to need the CPU for 4 milliseconds. Without any stop, and then they're going to make a stop, say okay, I'm going to do some IO work, and then I'm going to resume my CPU burst. So from this we can see that actually even though we run a lot of processes, there is on CPU. So if we come back to here, and so this is like we have, for example, we have four processes, like, and so they are, all of them are going to need the CPU. But what the thing is that, okay, when each of them needs the CPU, in most cases they are only going to need the CPU for use the CPU for very short period of time, just less than 4 milliseconds, and then they're going to release the CPU so that the CPU is able to execute another process for also a very short amount of time. And here this gives us the space to let the CPU rotate between among different processes in a very quick manner, so that we don't feel this rotation. We just feel like the CPU is running all of the processes all the time. So this is like most customers in the restaurant, they only need the waiter when they want to order something, or when they just want to say the waiter to take off the food, to take away some finished food, or take away some empty plates. So even though here, so with this being said, okay, even though we have maybe 10 customers in a restaurant, and we only have one single waiter, this waiter can just quickly rotate, so serve one customer for maybe 30 seconds, and then go to the next table, and then go to the next table, so that all the customers can be served. And here this gives us the motivation. So similarly over here, okay, we can design a CPU scheduling algorithm to let the CPU quickly rotate between all the processes, because even though when a process is asking for a CPU, in most cases it's only going to use the CPU for less than 4 milliseconds. And so here for human beings, okay, as long as the rotation speed each process takes less than 20 milliseconds, and then we just let the CPU quickly rotate between all these processes, we don't feel the rotation. So this is decided by our brain. Okay, we only have this kind of brain to accept things whose our brain can only handle rotations which takes longer than 20 milliseconds. If the rotation is less than 20 milliseconds, we can't feel that. So okay, and then this gives us the motivation. Okay, if we design a CPU scheduling algorithm to let the CPU rotate between other processes, and so if in most cases each rotation takes less than 20 milliseconds, people or the users are not going to feel the rotation. They just feel like everything is running, all processes are running, and this is the thing that we want. Okay, so so next, another thing that I want to talk about is called context switch. So what we mean by context switch is that, so here we have P1 who is using the CPU now, who is using the CPU now, who is, so the if C1 is running this the CPU is running process P1, and then for now CPU said, okay, I'm running you for long enough, I'm going to serve P2. So when the CPU switch between two different processes, we say and we see this job is we call this job context switch. So if you remember, when there is a context switch, so we need to be able to update the processor's control block, which just lists all the variable values, and okay, and also we have a program counter shows okay up to which line have we finished, so that next time when we resume the execution of a process, we know where should we restart. Okay, so actually the context switch, there is a latency, or actually the context switch takes time, and so we don't want to have too many context switches because each of them just take time. So here is the diagram that we see before. This is called the process state transition diagram. So I hope that you can still remember it. When we create a new process, it's in a new state, and then so when the process is ready to run, it goes to the ready queue, and it's going to be in the ready state. So and then so when the CPU is free, it is possible that the process grabs the CPU, and so then that it can go to the running state. And so when there is an interrupt, saying for example the process needs the user's input, and then so we say that there is an interrupt, so that the process goes back. There is a IO event, so that the process goes to the waiting state. Or if there is an interrupt saying that the CPU say okay, I'm running you for too long, now I have to serve the other people. So then it transits from running state to the ready state, and then after the process is finished running, it goes from the running state to the terminated state. Okay, so here before that, I just want to introduce that there are two types of CPU scheduling algorithms. The first category, we call them non-preemptive scheduling. So this type of scheduling algorithm is like, so after it assigns the CPU to a process, it will let the process take the CPU forever until the process says that I am done, I'm going to release the CPU. So which means that it's possible for a process to grab the CPU for a very long time until it finishes its CPU burst, or it just say I'm done. Whereas preemptive scheduling is like, so even after the CPU scheduling algorithm assigns the CPU to a process, and then so it says okay, I'm going to give you a certain amount of time. So when you reach this time, even though you are not finished, I'm going to let the CPU serve or take care of another process and then come back to you later. So this is can so in preempt so if we have a preemptive scheduling algorithm, we say that the process can be forced to give up the CPU when in most cases. So this is because of a timeout, meaning that it runs out of time. So back in 1980s, the mainstream scheduling algorithms are non-preemptive, this type, but it has a very big limitation. So that nowadays, after that, starting from 1990s, most operating system turn to use preemptive scheduling algorithms. So here I'm just going to use this figure to show the difference between preemptive and non-preemptive. So here you can see that for non-preemptive process, this a process can take the CPU for a very long time, like here. But if we have a preemptive CPU scheduling algorithm, basically each process gets a relatively fair share of the CPU. So each time when they grab the CPU, okay. So this is the difference between them. And also also when people design different CPU scheduling algorithms, we need to evaluate, okay, if this scheduling algorithm is good or not. Then we are going to need some uh, uh, criteria to determine what is good and what is not. So here are some metrics or criteria that we're going to use. The first one is called CPU utilization rate. It's like, so for what fraction of time is the CPU really running some process. We don't want it to just idle or wait for too long. And the second concept is called throughput. So it means that the number of processes that finish their execution within a certain amount of time. So we basically want to maximize CPU the throughput and CPU utilization rate. And also here we have turnaround time. So this time means that the turnaround time means that the time between a process submission and the completion. So, and also we have this called waiting time. It's like the time between a process submission and it started to be executed. So and also the other metric is called response time. It means the time between a process submission and the first output. So let me just explain these three different time in a relatively easier to understand way. So turnaround time means like let's just use this as an example. So let's just use the example of going to a restaurant. So the turnaround time of going to a restaurant means that the time between your enter the restaurant and leave the restaurant or finish your dinner. And so it's like the time between the process submission and completion. Waiting time means okay, so how long does it take for after you enter the restaurant and start to be served, okay, your first serve, you're firstly served, okay. So like how long does it take for the server to come to your table for the first time. And response time is like, okay, so the time interval between you enter a restaurant and you get your first dish, okay. So basically we want to minimize this three time, and most often we are going to use waiting time and CPU utilization rate. So here I'm just going to introduce four. Today I'm just going to introduce four or or five CPU scheduling algorithms in detail. So the first one is called first come first serve scheduling algorithm, and actually this is the most basic one. From the name we can tell what this scheduling algorithm does. So it always allocates the CPU to the process which enters the waiting list the first, and then that process is going to be able to take the CPU however long it wants, just until it finishes execution. And then so we're going to allocate the CPU to the second process in the waiting queue. Or so this is the general idea behind it. So here let me just give you an example. Suppose at time zero we have three processes ready to run, okay, P1, P2, and P3, and they are relative, or even though they are ready at the same time, there is an order between them. We say P1 is before P2 and P2 is before P3. So the CPU burst time for them are 24, 3, and 3, etc., etc. So here, so we basically want to figure out what is the waiting time for these processes. So to do that, we should draw a chart named Gantt chart. named Gantt chart. Gantt chart is pretty simple. So it's just like we use the x-axis as the time. This is the time, and so here we say that okay, because we're using first come first serve, and since P1 arrives first, we're going to allocate the CPU to P1 first. So P1 can takes the CPU first, and then it's going to execute after until it finishes its CPU burst. And so P1 takes the CPU from time 0 to 24. Okay, and then here next we're going to let the CPU execute P2. So P2 is going to take the CPU for 3 milliseconds. Here I'm just using the first time as milliseconds. So P2 is going to occupy the CPU from the time 24 to 23. And then the last one is P3. So since its CPU burst time is also 3 milliseconds, so it's going to take the CPU from the time 27 to 30. So here we need to figure out the waiting time for all these processes. So if you don't remember what is the definition of waiting time, we can say that it's the time between the process submission and start to be executed. So here all of them arrive. So the start time, the submission time for both of them are just at 0. Okay, just times 0. But for the time of first serve, okay, the time for them to be served first, P1 got served at time 0. Okay, P2 got served at time 24, and P3 got served at time 27. Okay, so the waiting time is really the difference. The waiting time is the difference between the time of being first served and submission. So for P0 for P1 its waiting time is 0. P2 its waiting time is 24. P3 the waiting time is 27. So then here we can just calculate the average waiting time as the sum of the 3 time divided by 3, which is the number of process, and here we got 17. So this is the first come first serve CPU scheduling algorithm, and it's relatively easy. Okay, so okay, so this is the first come first serve algorithm, and the next one that we're going to talk about is called shortest job first. So the reason why people design shortest job first is here, like you can see that suppose okay, when you go to a supermarket, so you go to a supermarket and you just want to check out. So it happens that you just buy two pieces of things, 2 items, like let's say just 1 milk and one bread, and now you want to check out. But when you go to the cashier, you just found okay, one person before you, and that person has 3 cards of items, hundreds of items. So like so here, yes, because in supermarket where the cashiers are using a first come first serve policy, so you have to wait a long time for the first person to finish his checkout, so that you can go to the cashier and be served next, and which ends up with a very, very long waiting time for you. So in contrast, if the first person, if the person before you is good enough, he or she would tell you, okay, boy, just come over, because you just have 2 items. I'm going to let you check out so that you don't have to wait so long, and I don't have to wait too long either, because you are going to finish your checkout very quickly. So both of you are happy, even though the person before you wait a little bit longer. Okay, So yes, this is the the how can we improve the over the first come first serve scheduling algorithm. That is that we are going to allocate the CPU to the shortest job first. Shortest the by shortest we mean that the process that has the shortest CPU burst. So here the general idea is that each process is associated with the length of the CPU burst. So when the CPU is available, the process with the shortest CPU burst is going to be allocated. So here again, let's say we have four processes. This is their CPU burst time, 6, 8, 3, and 7. All of them arrive at arrive time is 0. Okay, all of them arrive at time 0. So if we are using shortest job first, then we're going to allocate the CPU to the process that, and so with the shortest CPU burst time. And from this four, the one that with the shortest CPU burst time is P4. So P4 grabs the CPU first for 3 seconds, sorry, 3 milliseconds, and then so in the remaining 3, we found that okay, P1 is the shortest, so we are going to allocate the CPU to P1 for 6 milliseconds, and then at time 9, so we are going to allocate the CPU to P3 because its CPU burst time is shorter than P2, and last P2 is going to grab the CPU. So here for all of them, let's just check the waiting time. So for the waiting time is like this. The waiting time of P1, the waiting time of P1 is 3. Okay, the waiting time of P2 is right over here, 16, and the waiting time of P3 is 9, and the waiting time of P4 is just 0. So if we calculate the average waiting time, it's like this, 7 milliseconds. And people actually prove that shortest job first scheduling is the optimal one in terms of the average waiting time, because it always gives the minimum average waiting time. So this is guaranteed. So so some of you may say that okay, let's just use this one because this is the optimal one. This is the best we can hope. But the it's not going to be that easy. This is because before in most cases, before we execute a process, we don't know how long it is going to take, right? So this is really a chicken and egg problem. Without executing a process, you don't know how long it is, and without the knowledge of how long it is going to take, is going to execute, then so the shortest job first scheduling algorithm is not going to be able to work. So this is why in practice no one use this algorithm, because we don't have the knowledge of the CPU burst time of a process. So then people proposes different variations of the shortest job first algorithm, which is out of the scope of our lecture. And if you have the interest, you can read it by yourself. So basically, what it does is that it estimates. So from the past the history data, it estimates the CPU burst time of the processes. And so this is the general idea, so that it can just kind of like apply the shortest job first algorithm. And then so given that shortest job first algorithm is not going to be practical in real life, in real life, so people design another one named priority scheduling. Priority scheduling is like we associate each process with a priority, and actually when we learn the concept of process, we already see that, because we do see that each process is truly associated with a with the priority. And so then for priority scheduling algorithm, so what it does is that when the CPU is available, it allocates the CPU to the process with the highest priority. So here I'm just going to show you one example. Again, all these processes arrive at time 0, okay? Or arrive at time 0. And this is their CPU burst time, and this is their priority. So in this example, we're going to say that the lower priority value, lower value means higher priority. It's higher priority. So here we have 5 processes, and the one with the highest priority is just here. It's just P2 because it has the lowest value in the priority. So a low priority means, a low value means a high priority. So so here what it does is that it first allocates the CPU to the process with the highest priority, which is P2, and P2 is going to take the CPU for 1 millisecond, and then we're going to allocate the CPU to P5 for 5 milliseconds, and then it is P1 for 10 milliseconds, and then it is P3 for 4 milliseconds, and then we are going to execute P4 for 1 millisecond again. And here we can just get the average, we can just calculate the waiting time for all processes. For P1, its waiting time is just 6, and P2 its waiting time is 0 over here. P3, the waiting time of P3 is 16, and the waiting time of P4 is just 18, and the waiting time of P5 is right over here 1. So if we sum them up and divide by 5, we can see that the average waiting time for all processes is 8.2 milliseconds. Okay, so this is the idea of priority scheduling. The problem of priority scheduling algorithm is that it usually takes a very long time for process with a low priority to wait. Okay, and then it's possible that those processes with low priority may never be able to run. Okay, they're just stuck in a waiting list for forever. Okay, so then to solve the problem, before that, let's say all the 3 algorithms that we learned before are just non-preemptive. They're non-preemptive because once in these 3 scheduling algorithms, once the CPU is allocated to a process, it is going to it is going to run the full burst of that process and then is going to serve the other one. So it's kind of like we let a process grab the CPU until it is willing to give it up. Okay, and so here we're just going to learn the most important CPU scheduling algorithm named round robin. So in round robin algorithm, so this is the first preemptive scheduling algorithm that we're going to learn. Preemptive CPU scheduling algorithm. So the idea is that we're going to allocate a quantum. Okay, so we're going to use quantum to describe the unit of CPU scheduling. So it's like if we allocate this the CPU to a process, even the process can only take the CPU for the time of a quantum, and after it finishes one quantum, even though the process is not finished, it has to release the CPU, and so that we can let the CPU execute a different process, so that all the other processes do not have to wait too long. So this is the idea, and And this is the idea. Okay, so for again here we have assume that we have three processes arrive at time 0 and their relative order is just P1, P2, and P3. They have different CPU burst time as 24, 3, and 3. So assume that we are using quantum size as 4 milliseconds. So it's like so when we allocate the CPU to a process, so even though the process is not finished, it can only take up to 4 milliseconds and then give up the CPU. Okay, so let's do let's just work on this example together. I'm just going to go to this page and then add a page. Okay, so here we have P1, P2, P3, and then we have P1 as, so for P1 its waiting time is 20, sorry, its CPU burst time is 24, P2 its CPU burst time is 3, P3 the CPU burst time is 3. So here we see a quantum size is 4 milliseconds. Okay, let's work out the gain chart. So in the beginning we allocate the CPU to P1 because it's the first one. Okay, so we're going to allocate the CPU to it for how long? For just 4 milliseconds. Just 4 milliseconds for P1. Okay, so this is because the quantum size is 4. Even though P1 is not finished, you can only so grab the CPU for 4 milliseconds. So the remaining time of P1 is just the remaining time of P1 is 20. Okay, and then so we're going to allocate the CPU to P2. So P2. Okay, so because P2 only needs 3 milliseconds, so here we're just going to let P2 grab the CPU for 3 milliseconds, and so it releases the CPU at time 7, and then so the remaining time is just 0. So P2 finishes its CPU burst, and then we're going to allocate the CPU to P3. Again, it's only going to take the CPU for 3 milliseconds and finishes at time 10. So and then so we're just going to so from here we can see that only P1 needs the CPU. So we're going to allocate the CPU to P1 for quantum 4 milliseconds. Again, because only P1 needs to run. So P1 just grabs for another quantum for 4 milliseconds, and then for 4 milliseconds. Okay, so and this is the gain chart, and here we can see the waiting time for all the processes. Let's calculate their waiting time. For P1 its waiting time is 0 because it gets served at time 0. For P2 its waiting time is 4. For P3 its waiting time is 7. So here we can just calculate the average waiting time divided by 3, that is 3.767. Okay, and so here if we go back to the previous first come first serve scheduling algorithm, we can see that yes, we're using the same no, not over here, yes, here we're using the same numbers. The average waiting time is 17, but if we use round robin, the average waiting time reduces to 3.767, and this is a big improvement. So this is the gain chart that I described before. Okay, so this is the idea of round robin. Actually, in round robin algorithm, a very important thing is to decide, come up with an appropriate value of the quantum size. So here, if the quantum size is too large, so we are going to allow a single process to grab the CPU for too long. So this may cause the other processes to wait for too long. Whereas if we just reduce the quantum size to a very small number, say 1 milliseconds, then we are going to see a lot of context switches So, and previously we said there is a latency, or each context switch can take some time. So there is like, so you can take it as this way. We're just letting the waiter keep running between different tables, but end up with a very small amount of serving time at each table. So that's why we say that we usually it's very hard to decide a good quantum number and quantum size, and this needs some research. So, and actually this is a very hot area of operating system research. So here, this is our main topic, main content today. We learned the motivation of CPU scheduling algorithm, and also we learned 4 CPU scheduling algorithms. The first 3 are non-preemptive, whereas the last one is just preemptive. So okay, and here let's do a practice before we end this lecture. So I'm just going to add one slide over here, clear page, add a page. Okay, I'm just going to add a page. So the problem is here that suppose that we have 5 processes. We should arrive all at time 0, but with a relative order of P1, P2, P3, P4, and P5. And then we want to calculate the average waiting time and turnaround time when the following scheduling algorithm is applied. So yes, we all know what is waiting time, but some of you may forget what is the definition of turnaround time. Turnaround time means the time between a process is ready and the time when it is finished. Okay, so first let's check what is what's the result of first come first serve. First come first serve is pretty simple. Okay, so we are going to allocate the CPU to P1 first for 10 milliseconds. So from 0 to 10, and then we're going to allocate the CPU to P2 for 29 milliseconds. So which ends up at the time 39. Okay, and then we're going to allocate it to P3 for 3 milliseconds. So we finish at time 42, and then we're going to allocate the CPU to P4, so which for 7 milliseconds, 49, and then finally it is P5 for 12 milliseconds. Okay, so here we can just calculate the waiting time and say P1. So this is the waiting time and this is the turnaround time. Okay, the waiting time of P1 is 0. Its turnaround time is 10. The waiting time of P2 is 10. Its turnaround time is 39. The waiting time of P3 is 39, and its turnaround time is 42. For P4, its waiting time is 42. Turnaround time is 49. For P5, its waiting time is 49, and turnaround time is here is no, not 12. Sorry, this is not 12. This is actually 61. Okay, so if we take the average, and then we'll be able to calculate the average waiting time and turnaround time. Okay, and next let's see what if we use first come. What if we use a different one? We use shortest job first. Okay, for shortest job first, so we're going to allocate the CPU to the shortest the process with the shortest CPU burst. So first we allocated the CPU to P3, and then so from time, so because its CPU burst time is the shortest 3, so from time 0 to 3, and then it is P4 from time 3 to 10, and then it is just it is P1 from 10 to 20, and then it is P5 from 20 to 32, and at last it is just P2 from 32 to 61. So here again we can just calculate the waiting time and turnaround time for other processes. I'm just going to skip that, but you can check my following following slides for that answer. Okay. So, and then the last one is round robin. So if we use round robin with a quantum size 10, okay, let's see what is the result. First, we are going to allocate the CPU to P1 for 10 milliseconds, and then P1 is going to be done. So P1 is going to be finished. And then we're going to allocate it to P2 for 10 milliseconds. So P2 has a remaining time of 19 milliseconds. And then it's P3 for 3 milliseconds. And then it is P4 for 7 milliseconds. And then at last it is P5 for 10 milliseconds. 10 milliseconds. So P5 still has 2 milliseconds remaining. And then we're going to allocate the CPU to P2 for another 10 milliseconds. And then it is P5, so P2 still needs to run for 9 milliseconds, and then it is P5 for 2 milliseconds. So P5 is going to be done. At the last, we allocate the CPU to P2 for 9 milliseconds, and then for 9 milliseconds, and then P2 is done. So all the processes finish execution, and then we can calculate the average waiting time and also the average turnaround time. Okay. So if you follow this practice, you should be able to get a very good understanding of the CPU scheduling algorithms. So here, after this week, you are going to have your first homework, which is the about CPU scheduling algorithms. Okay. So it's not going to take too long, especially if you finish reading these sub chapters. If you want to read these sub chapters, it's going to take around 2 hours, and after that, it's going to take around another 1.5 hours for you to finish the homework. Okay, so it's not very heavy duty. So okay, so this is the lecture for